Hi everyone, thank you so much for taking the time to join me on my talk. Today I want to talk to you about Azure Confidential Computing. Now, confidential computing is a pretty neat but complex subject. Fortunately though, Microsoft and its partners are making tremendous strides in lowering the complexity, thus ensuring that this field becomes a lot more accessible. This is definitely something that I'm going to show you through the use of some demos. But first, let me introduce myself. My name is Thomas van Laere. I am a Microsoft Azure consultant. I help organizations with lowering their operational costs through the Azure platform and through the use of open source technologies. So what will I be talking about specifically? Well, I'm going to talk to you about some of the reasons why someone might want to take a closer look at confidential computing and what benefits it can bring to the table. I'll discuss how Microsoft defines confidential computing and the core infrastructure offers that they have. As part of some demos, I will also be deploying and messing around with some of those confidential workloads in the Azure cloud. Typically, I start my talks by explaining why exactly I'm talking about a specific subject in the first place, so I hope you don't mind that I'm continuing this trend. I believe that the first time that I had heard about Azure Confidential Computing was when Mark Russinovich spoke about it at Ignite 2017 during his Inside Microsoft Azure Data Center Hardware and Software Architecture session. Now, I must admit, though, that back in 2017, I did not think that Azure Confidential Computing was the sort of technology that I would ever get my hands on. A few years ago, however, I noticed that Microsoft had put out a blog where they wrote about a new set of capabilities that had been added to the compute platform. If I remember correctly, it was around November 2019, and the announcement had been made that Azure Kubernetes Service had this additional layer of data protection for their Kubernetes workloads. And somewhere in that blog post, they wrote that this additional layer of protection was achieved by running code on the CPU along with secure hardware enclaves. And at the time, I didn't really understand what any of this meant, but it intrigued me just enough to decide to take a closer look at it. And I decided to do that by taking a closer look at Azure Confidential Compute in general and to write about what I learned to the best of my ability, at least. Up until that point, confidential computing had always been a, blind spot for me. And in case you're wondering, Mark's Ignite 2017 session is still very interesting to watch. And having rewatched it prior to recording this session, I can say that much of the things that were mentioned about confidential computing are still relevant to this day. Although a lot of new additional and new advancements have been made, as we'll soon see. So why bother with confidential computing, and what does it bring to the table in terms of added security? Well, I think that confidential computing addresses two very important aspects. One aspect is related to an organization's business requirements, and the other aspect is related to technical requirements. Today, some businesses want guarantees that administrators, data center operators, or other third parties cannot access their data without their consent. And those businesses want to be sure that the cloud infrastructure doesn't contain any exploits that can lead to hackers abusing them. They also want guarantees that multi-tenant boundaries cannot be breached for services such as Azure App Service, for instance. Even though this is a difficult question to answer, it's not always wrong to think about it. Azure Confidential Computing makes it easier to trust the cloud provider. Ironically enough, this is achieved by reducing the need for trust across various aspects of the cloud infrastructure, like the one pictured here. Microsoft is striving to provide businesses with all the technical controls to isolate their data and to minimize trust for the host OS kernel, the hypervisor, virtual machine administrators, and even the Azure cloud personnel. Businesses are always on the lookout for ways to minimize trust in order to remain in full control over their data's lifecycle. There are still concerns surrounding data privacy, untrusted collaboration between multiple parties. Some markets or governments require that businesses must ensure that their data is subject to all different sorts of regulations and remain in a compliant state. And then there's also the overall trust that businesses have in the Azure platform itself. Now, the cloud has grown in popularity, and because of that fact, it allows you to do certain things in an incredibly efficient manner, all while being incredibly cost effective. And that being said, there are still plenty of enterprises out there that are hesitant to run their workloads in the cloud. Even though Azure has a comprehensive compliance coverage to meet all sorts of regulations, that doesn't always mean that they're free from vulnerabilities. Anyways, besides finding ways to mitigate some of these issues operationally, Microsoft has also made it a priority to find technical solutions. From what I was able to gather, current security models can adequately mitigate security risks that are typically associated with the storage and transmission of data, but they typically fall short when addressing the risk of exposing data as it is being processed. Now, more recent security models encourage the adoption of a more comprehensive protection model, one that mitigates risks across the data lifecycle, so from transmission to storage and usage. And this is something that can be achieved through Azure Confidential Computing. If we think about it in terms of Microsoft Azure, you may already know that the platform fully supports encryption at rest and encryption in transit, and it has done so for many years now. An example of end-to-end encryption is HTTPS and TLS, which can prevent data from being snooped upon inside of your network. So basically, it prevents hackers from reading data in clear text. And as for encryption of data at rest, Azure Storage Encryption Scopes and Azure SQL Managed Instance Transparent Database Encryption are two common examples. Customers can store their own keys in Azure Key Vault or Key Vault Managed HSM so that they can use it to encrypt data with their own private keys. If these two types of encryption are first-class citizens in your software or architectures, that's a good thing. You're already ensuring that parts of your data's lifecycle are protected. And although from what I've come to learn, we can take it one step further. Consider this: when we run a process or an application, it might load encrypted data from disk, then decrypt it in memory, and perform some sort of computation on it. And at this stage, the data is technically accessible to anyone. And it really is. And we will soon see this in a demo that it's actually accessible to anyone. So there is still this missing piece that we should take into consideration when it comes to protecting our data, which is encryption of data as it's being processed. If we take into consideration all those business requirements and the confidentiality guarantees of encryption of data in use, you can see that it enables some new scenarios in the Azure cloud that weren't always easy to tap into, even with on-premises environments. We can use it to defend ourselves from malicious operators and protect against our data being read from outside of our boundaries. And additionally, we could use these technologies to securely share data with other parties in order to perform things like federated learning, all while keeping that data confidential. Azure Confidential Computing can help you get to a place where you can get significant confidentiality guarantees similar to a private data center, but with the scale and the flexibility of the Azure platform. And this can pave way for businesses to tap into new Azure features without worrying too much about data privacy or potential compliance issues. This can make Azure Confidential Compute its value proposition very compelling to those who might be on the fence about moving sensitive workloads into an Azure data center. What are some of the options then that we have if we want to protect our data that's in use? There are a few approaches to doing this, of which I will highlight two. The first approach is called homomorphic encryption, and it's not actually part of what Azure has on offer in their confidential compute portfolio, but for completeness sake, I figured I'd briefly mention this. The main idea behind this concept is that all inputs have been pre-encrypted and that you will act on that encrypted data. The data is essentially never revealed while you're performing computations on it. Though from what I've read, this approach is fairly limited in terms of what you can do, and especially when you go down the AI and ML path. It's still very computation intensive, and performance is still an issue, though that is being addressed. However, it's a type of technology that is still evolving, like so many others in this space. So who knows? Maybe we'll see something pop up in the near future. Microsoft is already working on something. It's called Project Seal. And yeah, you can definitely take a look at it if you want to learn more about homomorphic encryption. But as I said, there is another way through which we can protect data that's in use. This method is a cornerstone of Microsoft's confidential compute offering. The mechanism used for achieving these types of confidentiality guarantees is through something that is called a hardware-based trusted execution environment, or TEE for short. But what exactly is a trusted execution environment? Well, at a high level, it's basically a secure environment where we can run some code. And by opting to execute these computations inside of a TEE, we can prevent unauthorized access or modifications of the code and the data while it's in use. But because the environment must be trusted, they must also provide certain other properties. There are 3 properties that have been defined by the Confidential Compute Consortium that a TEE has to implement. That's data confidentiality, data integrity, and code integrity. Data confidentiality basically means that unauthorized entities aren't allowed to view the data while it's in use within the TEE. And data and code integrity means that unauthorized entities cannot add, remove, or modify any of the data or code within the TEE. So basically, a trusted execution environment is a tampering-resistant environment that allows you to safely run your sensitive workloads inside of it. Again, you could probably compare this to something like a black box system that is protected by a TEE provider like ARM, Intel, or AMD. And the provider creates the black box, which provides isolation from specific levels of the system. And as we'll soon see, depending on the provider's implementation of a TEE, that might mean different things. Before we dive deeper into those TEEs, it's important that we take a look at some of the foundational components for confidential computing, and by extension, trusted execution environments. There's a few, and we'll start with the hardware root of trust, which is essentially a hardware-based key to ensure that data is protected and anchored into the silicon. And for businesses, this means that the trust is rooted to the hardware manufacturer, and even Microsoft operators cannot modify those hardware configurations. This does mean that you'll need to place some trust in the silicon provider, so that's Intel or AMD. Another key ingredient is remote attestation, and this allows you to directly verify the integrity of the trusted execution environment. You can verify that both the hardware and the software on which their workloads run are approved versions and secured before allowing them to access data. Third component is trusted launch, which is a mechanism that ensures that Generation 2 Azure virtual machines can boot with authorized software, and that uses remote attestation so that you can verify the state of your VM's boot chain. And it's a feature that is actually available to all VM SKUs that run Generation 2 Azure images, including confidential machines. So Trusted Launch brings secure boot and VTPMs to help defend against rootkits, bootkits, and other malicious firmware. We will dive deeper into this in a moment. Then there's also memory isolation and encryption, again, to ensure that the data is protected while it's being processed. And Azure offers memory isolation for VMs and, by extension, containers and applications to meet various needs. Hardware-based encryption helps with preventing unauthorized viewing of the data, even if there are people with physical access in the Azure data center. And the final one is secure key management. This ensures that keys stay encrypted during their lifecycle and release only to authorized code. And this is something that is achieved with Azure Key Vault or Azure Key Vault Managed HSM. But let's zoom in on one of those foundations real quick. Remote attestation is something that helps us to prove that something is running in the intended operating state. It is a process by which one party, typically the verifier, assesses the trustworthiness of a potentially untrusted peer, the attester. And remote attestation provides verification for three things. That is the application's identity, its integrity, in other words, that it proves that the code has not been tampered with, and that it is running securely within a trusted execution environment on some trusted execution environment enabled platform, right? So something from AMD or Intel. Again, we'll take a look at those platforms in a minute. So in a nutshell, using this technique, a remote party can verify that the correct software is running inside of a TEE. What does Microsoft offer us in terms of trusted execution environments? When choosing a confidential VM SKU, you can actually choose from two CPU flavors on Azure. Either you pick a CPU that supports Intel Software Guard extensions, so that's Intel Sgx, or you pick one that supports AMD Secure Encrypted Virtualization, Secure Nested Paging, so that's AMD SEV SNP. When you pick a SKU, that will ultimately boil down to how much of a trusted computing base you're willing to take on. The more code that we end up running inside of a trusted execution environment, the larger the trusted computing base becomes. And a trusted computing base refers to all of the system's hardware, firmware, and software components that provide a secure environment. And components inside of this TCB are considered critical. So if one of these components is compromised, the entire system's security may be at stake. So a lower TCB means higher security. Now, both vendors essentially have a set of CPU features that allows them to offer confidential computing capabilities. However, even though both technologies lets you create TEEs, both are used for widely different scenarios. Sgx is a feature for a specific set of Intel processors that lets you create application enclaves. And these enclaves can keep data encrypted as the CPU is processing it, and nothing and no one is able to view the data from the outside. The trusted compute base here is rather small because you're only placing your trust in your application code and the Intel chip that it runs on. Now, in contrast, AMD SEV SMP is a technology designed to isolate machines from the hypervisor, or at least SEV is. And in essence, the entire state of the virtual machine is encrypted. And AMD's implementation of a trusted execution environment offers a much more flexibility compared to Intel Sgx. However, because the entire operating system is inside of the TEE, the trusted compute base is substantially larger, and it might be more susceptible to all sorts of attacks. Many of Microsoft's sessions on the subject of confidential computing that I've seen talk about the trust ladder. The basic premise of the ladder comes down to this. The higher up the ladder we go, the more our security posture is strengthened to some extent. So let's take a look at that ladder. Keep in mind that as we go through these rungs, there might not be a one-size-fits-all answer. As with a lot of application modernization efforts, where you'll land partially depends on the requirements of your application and the constraints of that code base. The more code that is put inside of a trusted execution environment, the more vulnerable your setup might become due to the larger trusted compute base. Keep this in mind. So let's start with the option that gives you the best posture in the lowest TCB, and that is hardware enclaves with Intel Sgx. I personally think that if you want to take advantage of an Intel Sgx powered virtual machine, you will need to be comfortable with refactoring parts of your application code to take advantage of Intel Sgx. And a framework such as the Open Enclave SDK can be a tremendous help in jumpstarting your development on this front. With confidential containers, though, you could make things a little easier for yourself, because this option gives you two separate methods. You can lift and shift existing container images and run them inside of an enclave without having to modify any of the source code or perform recompilation. And as you can probably imagine, you're going to have to wrap your existing container image with the Intel Software Guard extension's runtime in order to let an application run inside of a TEE, inside of this enclave. This can be as simple as pointing your container image to a different base image, but it really is specific to the wrapper solution that you end up using. So Microsoft has listed quite a few partners on the documentation website if you want to check those out. I will also be providing a link at the end of the session to that list. Then there's also enclave-aware containers, which are just Sgx applications that run inside of a containerized environment. And this is a great option when you want to run existing Sgx apps via a container orchestrator like Kubernetes. Confidential containers have a strong security and compute isolation, along with the same lower trusted computing base compared to the other solutions. A confidential virtual machine is, as we discussed, much like what you're used to using when using any other virtual machine. The confidential VM runs an operating system like Windows or Linux without having to make any major modifications to the OS, or at least you don't have to make any modifications to the OS. An important thing to keep in mind is that the trusted computing base is much larger when using a confidential VM. On one hand, you have to place all of your trust in the kernel and the user code on that VM. On the other hand, you will be able to perform tasks with the tools that you're familiar with. It goes without saying that this is probably the easiest way to hop on board of the confidential compute train. And the last technology that I will mention is Trusted Launch for Azure VMs, which is one of those key foundational components of trusted execution environments and provides your VM with its own trusted platform module instance. The Trusted Launch capability comes at no additional cost and is available even to most non-confidential VM SKUs. What makes Trusted Launch so interesting? Well, it consists of multiple security technologies, such as Secure Boot and a virtualized Trusted Platform module, that all operate in tandem. And by deploying virtual machines that utilize Trusted Launch with Secure Boot and VTPM enabled, you can be more confident in the fact that your VM's boot chain has not been compromised. Secure Boot provides a way to guard against sophisticated types of malware that typically run in kernel mode and are hidden from the user's site. As the VM boots up, Secure Boot checks the signature of each piece of boot software, including UEFI firmware drivers and EFI applications, and the operating system. If Secure Boot detects a compromised component in the boot chain, a cryptographic signature won't match and your VM will not boot. Then with the VTPM, this enables attestation, the concept that we saw earlier, by measuring the entire boot chain of your VM. And this process does not halt the boot process. It only computes the hash of the next object in the chain and stores the hashes on the VTPM. Now, if this process fails, an alert will actually be issued to Azure Defender for Cloud, and that is something that we will see in a demo. Let's fire up the Azure portal. So let's deploy a Trusted Launch virtual machine then. It's very easy. You just use the exact same tools as you normally would. Let's name this Trusted Launch VM. I don't need any infrastructure redundancy for this demo, I'm going to pick a standard general purpose compute non-confidential VM. So again, Trusted Launch works with all Gen 2 virtual machines. So if we go into the security type dropdown and select the Trusted Launch virtual machines, then we will be able to use a Trusted Launch virtual machine. Another thing that I want to point out is that there's the security features here. If you click on it, it's I think it's pretty well hidden. I've missed it a couple of times, but this basically allows you to enable or disable secure boot, the VTPM, and integrity monitoring. So integrity monitoring is actually the part that is going to do the attestation and the verification of your virtual machine. And also it's going to issue alerts to Defender for Cloud. So if you want to use that, keep all these enabled. So again, for the purposes of the demo, I'm just going to use some really bad security practices. Even though this talk would lead you to believe otherwise. I'm also going to use Cloud Init to set up my VM real quick. So I'm just going to pull in some packages, and then I'm going to clone this Git repository into the virtual machine. And then I'm going to connect to it with Visual Studio Code. So let's do that real quick. So Cloud Init has been enabled, and Trusted Launch has been enabled as well. Secure Boot, VTPM, and integrity monitoring. So that's great. Again, this comes at no additional cost, so you can just deploy this if you're using Gen 2 virtual machines. But again, you always want to check whether or not there are some limitations. And well, there's a couple of features that aren't supported. So if Azure Site Recovery is like a big requirement for you, yeah, you should probably not be using Trusted Launch then, or I don't know, maybe check with Microsoft on what the status might be of this feature. Okay. That VM should already be visible, I think, in the portal. There it is. And it's still saying that the integrity monitoring is disabled, but that's because the extension is probably wrapping up. So yeah, that is going to take another minute. So I will just fast forward until this is done. And now my Cloud Init file should have pulled in my Git repository. And there it is. And so I'll just copy this session/session. And I'll copy the demos, the Trusted Launch demo, and the evil module. And I'll copy that. And now I can open this folder right here in VS Code. There we go. So I basically have this really simple kernel module written in C. And I'm going to use this. I'm going to build this and stick it into the startup chain. So I'm going to add this as a driver. And you'll see that secure boot is actually going to prevent us from doing that. And I'll also disable secure boot since we can do that. And I'll try again, and you'll see that the module will load that time. So let's try this. The only thing that I'm going to do here is I'm going to use my notes because I don't want to be typing all the time. So I'll just build this. Okay, and we should be able to see that the kernel object has been built, so that's cool. And again, secure boot is enabled on this machine. So if we try to insert the kernel module, it'll actually say that the operation was not allowed. And that is actually secure boot that is going to block that. Now, if we make it so that our driver boots up along with our machine, then we can do some very interesting things. So let's try that. And now I also have to clear the mod probe cache. And if I reboot the machine now, you'll see that it's actually going to prevent the module from starting up. So we'll just wait for the machine to reboot. And now when we try to read from the kernel ring buffer, it's not going to mention anything. If we try to insert this again, we'll get the same result because secure boot is still enabled. Now, we can also disable secure boot. So if we just shut down the VM, go into security type, and disable secure boot here, and save it. And we can actually do this while it's deallocating. It doesn't seem to be a bad thing, so there we go. It has been stopped. If we restart it, you will also get a notification, by the way, that secure boot has been disabled rather, if we go into Defender for Cloud. But that is going to take a little while, I think. So here we have an example of what this is. Your virtual machine failed attestation because secure boot is disabled. So again, this is the alerting in action. And that is also why you need that extension. So let's switch back to the VM. Okay, so secure boot has been disabled. If we switch back to VS Code, do another reload here. Now, if we check, yes, secure boot has been disabled. And if we try to insert the module again, hey, it'll say that the file already exists. So that means that it was loaded on start. And as you can see, if we just do this with case sensitivity enabled, you'll see that it's actually loading the module now because we disabled secure boot. So again, secure boot is very useful for preventing these types of drivers from ever being activated by accident, or if it's being done by a malicious insider. Confidential VMs provide the easiest way to onboard legacy workloads in order to achieve confidentiality. This essentially enables businesses to lift and shift existing applications without having to learn a custom application programming model or to refactor applications. On top of this, confidential VMs further remove Azure functionality and operationally from the trusted computing base. At a high level, you can take an off-the-shelf operating system and stick it inside of a TEE. However, because the entire operating system is inside of the TEE, the trusted computing base is substantially larger, and thus it might be more susceptible to all sorts of attacks at the OS level. So it goes without saying that you should continue to use best practices when it comes to keeping your systems up to date, applying security patches, and keeping your application dependencies up to date, etc. And then if we zoom in on AMD's technology, SEV-SMP, which is used to create this trusted execution environment, you can see that it is built using a layered approach to achieve these confidentiality guarantees. And it begins with SEV, or Secure Encrypted Virtualization. And this isolates the VM from the hypervisor, which helps it to keep the data in use encrypted. And then there is SEVES, or Encrypted State, that ensures that guest VM CPU register states are also encrypted, and this helps to ensure that on each host to guest transition, these register states cannot be read or modified. Then there is SNP, or Secure Nested Paging, and this works in tandem with these other two technologies, so with SEV and SEVES, and it will provide confidentiality guarantees and integrity protection of the virtual machine's memory, amongst other things. So does this mean that everything inside of the confidential VM is encrypted? Well, not entirely. There is still a portion of shared memory that must remain unencrypted, and this is typically used when communicating to resources outside of the confidential VM. So inbound and outbound data must be placed in this shared memory and will be unencrypted. So you still have to use all of the other existing encryption technologies, so especially in transit. So things like TLS are still important. Due to the way that SEV-SMP is used to protect data in use, AMD actually recommends that you pair the technology with a full disk encryption solution. And now Azure already provides encryption at rest out of the box. However, it's not entirely the same as full disk encryption, or FDE, or as it is now called, confidential disk encryption. When you first enable confidential disk encryption, the OS disk will become fully encrypted before the first boot. So you have to enable this as you're deploying the VM. Whenever you boot the VM, Azure Attestation service will actually verify whether the disk is in a healthy state or not, and if it has been assigned to the correct VM. And these confidential virtual machines, again, the SKUs that you can use with these AMD SEV-SMP machines typically start with the DCA or ECA prefix. And if you're ever on the fence on whether or not you should pick this type of machine, you have to think to yourself, you have to go with this technology if you ever end up thinking, for compliancy reasons, Microsoft cannot touch anything that is running inside of my virtual machine, but I do trust the operating system and the virtual machine administrators that have access to the machine. So those can be your own virtual machine administrators that are inside of the business. Okay, so back in the Azure portal, and we'll actually do the exact same thing as we did earlier. We'll just create a new virtual machine. There we go. So we'll name this confidential VM. Select East US. You can also deploy this in West US and other regions if you wanted to. And we do not need any infrastructure redundancy. and we'll set the security type to confidential virtual machines. So that's on top of trusted launch. Again, you can change the security features here if you wanted to. And we will actually need to enable secure boot if we want that confidential disk encryption as well. You can also choose between Windows and Linux images. And again, if you want to do that, you just go into the marketplace, you filter the security type by confidential. And then you can select Windows Server 2022 or 2019, or Ubuntu Server 2004. I'm going to choose that one. And then for the size, again, if you go into the size selection, you have to select the DCA series, so everything with an AMD processor again. So we will select this one. We don't need the temp storage, so that's fine for a demo. Again, I will change this to password. Okay. And by the way, the costs for these virtual machines are actually quite all right in my book. I'd say they're about on par with the other virtual machine prices. Again, this is what I would expect from this type of VM SKU. So a lot of bang for your buck there. And if we take a look at disk, you'll see that enable encryption at host is not available, but confidential compute encryption is. So we can enable that, and then we can choose either a platform managed key or a customer managed key. We'll go with the first one, and that's fine. And everything else is fine as well, except I'm going to use Cloud Init again. Let's see here. Again, I've also included a bicep template if you want to deploy the sample yourself. So in here I have the Cloud Init file ready to go. So I'll walk through that one in just a second. Just kick things off here. There we go. So again, the security type is confidential virtual machine. Secure boot has been enabled. The VTPM has been enabled. Integrity monitoring wasn't an option to enable. But I'm sure that will become available quite soon. I'm looking for the confidential disk encryption, but we did enable it. So I'm just going to hit create. Now what I'm doing here is I'm actually going to install some packages again, and then I'm going to clone the sample repository. This is a different one. This is actually a fork that I made of a sample that Microsoft provides in order for you to perform guest attestation. And the only thing that I changed was I modified a URL that is pointing to the Azure Attestation service, so that I'm using an actual production endpoint instead of a test endpoint. So we can perform guest attestation in a minute. I'll just wait until that finishes. All right, so it's completed the deployment, and now if we take a look, we'll see that everything has been provisioned correctly. If we go into the disks, you can see that there is server-side encryption with a platform managed key and a confidential VM with a platform managed key. So if we click on the OS disk and head on over into encryption, you'll see that it has enabled confidential disk encryption. So again, those additional partitions have now also been encrypted before the first boot. And whenever our VM starts, the Azure Attestation service is going to attest to the fact that this disk is in a healthy state and that it has been associated to the correct VM, which is this confidential VM. And now, if I connect to this machine, I'm going to do that again with Visual Studio Code, but you might as well do it through terminal if you wanted to. So I'll SSH into it. There we go. Hit connect. Yes, I want to continue. There we go. So we're in. Let's take a look. Yep, everything has been provisioned correctly. Now I'm going to copy the confidential computing CVM guest attestation folder. There we go. I'm going to copy that one. Oh. Yep, there it is. And I can open this up now in VS Code, so we can take a look at what is inside of it. So again, there is a sample client zip, but that is not going to work because I had to make some modifications to this URL. Ideally, this is something that you would pass in as an argument for the into the binary, but it's been hard-coded for now, so we'll just roll with it. Let's open up the terminal. Now, if we make this all right, we need to use CMake for this. Hold up. CVM Linux. CMake. There we go. Now it's built the attestation client, and when we run this, we will see that it returns a token. And this is just a plain old JOT token. So if we copy this maybe into a new file, we might be able to see it better. Or we could actually use one of those online JOT decoders. But again, don't do this in a production environment. You can paste it in here, and then you'll be able to see that it contains a lot of information here in the payload. So let's just copy this. And now you'll be able to see that indeed this VM is an Azure virtual machine, and that it is using SCV SMP, and that it is a compliant CVM, amongst other things. Again, you probably could have just used this result and decoded the base64 string, maybe split it according to all these dots. So everything up until the first dot is a header, and everything beyond it up until the next one is the payload data. So I probably could have done it that way as well, but I did it differently. So that is confidential VMs in a nutshell. Okay, so I've also gone ahead and deployed a Windows virtual machine, a confidential virtual machine. Again, just to prove to you that these virtual machines are really just the same as any old virtual machine that you've been using up until this point. So let's just download the RDP file, fire up remote desktop, and again, this is going to take a minute to load up. But as I mentioned, you can just pretty much use all the tools that you're used to. So again, PowerShell or any other tool, it doesn't really matter. The only thing that is different here is that the fact that it's running inside of a trusted execution environment. And even if Azure administrators were to take a memory dump of your VM, they would not be able to decrypt the contents of the memory because it's all encrypted. So yeah, and here as well, if I use msinfo32, we can also see that EMD SCV SMP has been enabled. Again, this isn't the same as performing attestation. As we saw in Linux, you could use that same sample, build it for Windows to perform guest attestation if you wanted to. But Linux just gives me a little more flexibility in terms of demos, so that's why I use Linux to perform the guest attestation. Again, same old machine, just running inside of a trusted execution environment. So yeah. All right, let's take a look at VMs with application enclaves powered with Intel Sgx. So Intel Sgx is a feature for a specific set of processors that lets you create enclaves. Sgx enclaves are a hardware-based trusted execution environment solution. And this is why it only works on Intel Sgx capable processors. These enclaves can keep data encrypted as the CPU is processing it. An operating system or hypervisor can't even view or access the data, so the enclave is completely isolated from the host system. This also implies that your very own virtual machine administrators cannot gain access to any of this data. Even Azure Data Center administrators who might have physical access to the box that your VM is running on cannot access that data. Intel Sgx isolates its encrypted memory from all software on the VM, except for the application code inside of the protected Sgx enclave. Enclaves get an isolated portion of processor and memory space, and code and data inside of the enclaves are inaccessible to the outside and cannot be tampered with due to the CPU blocking off the access. The data cannot go out of this box in an unencrypted form. So then what does this actually look like? Well, your application is going to be partitioned into two parts, one trusted and one untrusted. When your application runs, it will create the enclave, which will be placed into a protected memory region with restricted entry and exit locations that are defined by the developer through a call gate or a proxy code like Laere. The entry location is called through a trusted function, and the enclave executes a chunk of code. The enclave code, as well as the data inside of the CPU parameter, runs in the clear. Enclave data that is written to memory will be encrypted and integrity checked. The trusted function will eventually return a return value, and your application continues its normal execution. Enclave data remains in the encrypted memory region. So could you stuff an entire app into an enclave? You could, but whether you should is something that you will need to determine for yourself. Again, this boils down to how much trust you're willing to place in your codebase, and perhaps some of its dependencies. Now, Microsoft Azure provides a few SKUs that will allow you to use those trusted execution environments, those SGX enclaves. Virtual machines with the SKUs that are associated with the Intel Sgx features all start with a DC prefix. So not DCA, but just plain old DC. And you should pick Intel Sgx if you're ever thinking that for compliancy reasons, you can only trust your application code and the Intel processor that it runs on. And if you do not trust the operating system or any of the operators that might be managing the machines. So again, only your code and the Intel chip, not the operating system nor the operators. Switching back to the Azure portal, we'll just deploy this SGX enabled machine, so we'll just call it SGX VM. Again, I'm not too concerned about the naming conventions here for this demo. No infrastructure redundancy required. And now, since this is a different implementation than a confidential virtual machine, where we place the entire operating system inside of a trusted execution environment, we're actually going to be using trusted launch virtual machines. Again, we're going to run our code inside of an enclave, so inside of that trusted execution environment, and then we can actually just use the trusted launch capability. If we were to pick confidential virtual machines, we would not be able to select the Intel Sgx SKU. You could even use a standard security type if you wanted to, but I'm going to use trusted launch. So that is fine. I'm going to deploy a Ubuntu server. Again, the Azure user. There we go. This is fine as well. Again, we will not be able to select confidential disk encryption because it is not really a confidential VM. And I will open up my Cloud Init file again. And this is a bit larger, a bit more than the previous ones, but that's okay. Oh, I have to enter the password twice, of course. Review and create, and that should be okay. Yes. Cloud Init, yes. Okie dokie. Again, what this is going to be doing is installing a few packages, and it's going to install everything that it needs in order for it to run the Open Enclave SDK. It's also going to install a tool called scanmem. We're just going to use that to change, or at least to try to change, a value of a variable inside of our enclave. So this is based on the getting started guide inside of the Open Enclave SDK. This is actually going to do the exact same thing, except for installing the SGX decap driver. If you wanted to use a more recent one, you probably could. But I'm going to go with the one that is installed along with the SGX VM. So I'll just skip ahead to where this has been deployed. Okay, so the VM has been deployed. Even though this message is saying that there's an issue, it's doing just fine. So the security type is set to trusted launch. We've enabled trusted secure boot and the VTPM and integrity monitoring. And as you can see, the extension has been deployed as well. Okay, so we are using a DC series VM. That is important, that you always deploy a DC SV2 or a DC SV3, because those are the ones that contain the Intel Sgx features. So I'm going to switch to VS Code here. I've actually gone ahead and connected to my VM. Let's see, everything has been installed correctly, so Cloud Init was still running. I skipped ahead as well, but it should be completed now. Okay, so that's fine. So I'm going to copy this directory. Session, just the Enclave demo, the Open Enclave sample. Okay, and now I'm going to open that folder up. There we go. Increase the size a bit here. Okay, and as you can see, there's two folders here, the Enclave folder and the host folder. Again, this is the untrusted part of the application, so the host is the untrusted part of the application. Then the Enclave obviously contains the Enclave code. Doesn't really do much. It's going to create a value in memory. So on the host end, is going to create this value, and inside of the Enclave we're going to do the exact same thing, except we're going to make a different value. And then we're going to halt the process by calling back into the host to perform a read key, so or a get car rather, which is going to stop the process and just wait until we we hit enter, and that will give us some time to mess around with it. So I will just build this sample. So I'll just make a new directory, cd into it, cmake all the files, and then make the binary. Okay. Also, this is the EDL file, so that is going to generate that proxy layer so that you can actually call into the Enclave from the host, and you will also be able to call into the host from inside the Enclave, but only if you list all of the functions that are available. And then this is obviously going to map to this one here. Okay. So everything has been built. Okay, so if we want to run this, we can actually just reference this file here. So we have to start with the host file, or the host binary rather, open Enclave sample host, and build Enclave sample open Enclave sample dot signed, or Enclave dot signed. And that is actually going to run the process. And so again, this is just going to show us the values as the process is starting, and then it's going to wait, and then we can make some changes with scanmem, and then it's going to print these values again. So if we run this, maybe open up a new terminal here. make this a bit smaller. Use scan mem. It is actually going to open up the process. Then if we search for our value, so if we search for the value inside of the enclave, it's not going to find anything. So if we search for this value, of course that's not going to work because we need to run this as sudo. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it finds 0 matches. Okay, so if we reset the tool again, and we look for this one, it will also find nothing. Of course, that's not the correct one. We have to do it in reverse. So this way. And now we have one match. And what we can do now is we can write to that address if we wanted to. So I have to list it actually first. And this is the address that our integer is set to. And the fact that we're just typing this number in here is because when scanmem starts up, it defaults to searching for integers. So that's why it has found it. If you wanted to perform things like string search or something, then you would have to change the type in the options, but that is beyond the scope of the demo, of course. So if we write to this one, we tell it that it's an I32. And then we can just write all zeros to it. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. Bad data type, I32. There we go. If we switch back to the enclave and hit continue, you'll see that it's actually changed the value, but again, we couldn't find the value for the variable that is running inside of the enclave because it is encrypted. So that is a nice way of demoing that these confidentiality guarantees are actually alive and well inside of this enclave. And again, you don't have to use Open Enclave because this is, I understand that this is very low level SDK for building enclaves. So the easier approach would be to just use the Intel Sgx runtime and wrap your code base inside of or with a container image. That is going to run the Intel Sgx runtime for you so that you can load your entire application into an Sgx enclave. But behind the scenes, this is actually going to do the exact same thing as you see here. So again, it's going to split up the application into a host or an untrusted part and a enclave part, which is going to contain all of your application code there. So that is how that works. All right, and with that, we've gone through some of the ways that you can use Azure Confidential Computing using infrastructure as a service offerings, but it doesn't end there, right? There's still a whole bunch of services that are worth checking out. For instance, Azure SQL has DC series hardware, which is required if you want to use always encrypted with secure enclaves. There's also the Microsoft Attestation service. It's a remote attestation service for validating the trustworthiness of trusted execution environments and, verifying the integrity of the binaries that are running inside of the TEE. And if you'd like to spin up your own instance, you can totally do that. There's also Iot Edge that supports confidential applications that run within secure enclaves on IoT devices. And that is also one of the targets for the Open Enclave SDK. So with Open Enclave, you can actually target IoT devices that run on ARM Trust Zone. And that way you can use the skills that you've learned with the Open Enclave as the SDK on this other environment. And there's also the new NCC series virtual machine SKU in private preview for running confidential GPU workloads. Now, there's probably one more important question that needs an answer. Are trusted execution environments the be-all and end-all of security? Well, I don't think so. I think that very clever people will always come up with really intricate ways of breaching security boundaries. But I think that having a layered approach to security can certainly help, and I believe that TEEs can be a very useful additional layer to add to this mix. To summarize, confidential computing can provide you with similar guarantees that you know from your traditional data centers, but in the Azure cloud. And this opens up many new scenarios where you can place different levels of trust. And on a technical aspect, Trusted Launch, a feature that is available to all Gen 2 images, comes at no additional costs that you can use when deploying new Azure virtual machines. If you want to lift and shift existing legacy workloads into a TEE, you can do so with confidential VMs that are powered by AMD SEV SNP, which just, lets you run your existing workloads inside of an operating system that has been placed inside of a trusted execution environment. If you want to take advantage of Intel Sgx enclaves, I would suggest having a look at the partners or open source enablers to jumpstart your development and maybe run some existing applications inside of an enclave through containers. And all of these features are either free or don't really cost that much. In my book, all of these features seem very cost efficient. So if you want to learn more about Azure Confidential Computing, I've included a link to the official documentation website, which is an amazing source if you want to get started with confidential computing. I've also added the link for the solutions that the Microsoft partners and open source communities have come up with. And I've also added a link to the Confidential Computing Consortium, which is a project community at the Linux Foundation dedicated to defining and accelerating the adoption of confidential computing. And I've also just wanted to add this link to my own blog if you want to learn more about confidential computing and maybe learn about some of the bumps that I've encountered while I've been going through my confidential compute journey. Feel free to have a look at my website and feel free to take a look at those blogs. And with that, all there is left for me to say is thank you for sticking with me. I hope some of the things I discussed were insightful to you, and I hope that it inspires you to mess around with confidential computing. All right, goodbye, take care.